Welcome to the Minelab Expert Series. Dive into the world of metal detecting with us as we tackle both its basics and intricacies, all while posing tough questions to the Minelab engineers themselves. Join us in this thrilling quest beneath the surface of metal detecting. Let's meet the Minelab experts who will be sharing with us today. We'll be talking to the General Manager of Engineering, Mark Laurie. Mark is an electronics engineer who has worked with Minelab for over 13 years. Mark was originally an R&D engineer on the CTX 3030 and GPZ 7000 and was also responsible for leadership on both Equinox and Manticore. We'll also meet Phil Beck, the General Manager of Product Marketing, Customer Care and Quality. Phil is an electronics engineer who has worked at Minelab for more than 20 years. Phil began work on Minelab's countermine projects and later worked on both GPZ 7000 and CTX 3030. Paul C. is a Minelab expert from Lincolnshire in the UK. Paul has been detecting for over 20 years and has trained hundreds of people at rallies and events in addition to entertaining hundreds of thousands of people on his various social media platforms. Paul has used pretty much every Minelab machine that's been released over the last 15 years and is a positive and well-respected presence in the UK detecting community. Hello everyone, welcome to our Minelab Expert Series. I want to thank everybody for joining us today. We're going to kick straight off, and today we're talking about how a metal detector works. So if I can just ask straight over to Adelaide, how does a metal detector work? So I know the basic components and the basic parts, but I don't really know, even though using one, I don't really understand the functionality of it. So how does a metal detector work?
Okay. Thank you. So basically, if you take an Equinox, it's one of our Minelab detectors, and I'm just going to quickly walk through all the parts of it before we start talking about how each part works. So you've got what we call the coil, which is the sort of disc-shaped thing at the end of the shaft. That's the main sensor of the detector that collects the information from the ground. And then you have the signals from that going up the cable along the shaft, and that goes to the control pod or control box. That's where sort of the brain or the engine of the detector is. That's where the user interface is, that the user will interact with the keypad and be getting information back to tell them whether to dig something out of the ground. And it's also where the audio is coming out of the detector. So you've got the coil down the end, you've got the control box, and then mounted on a shaft. In the Equinox case, it's an aluminium shaft that's telescopic. There's various other options on other detectors, carbon fibre. And that can be adjusted usually sort of into some fixed positions, and you can change the length of it depending on your height and your preferences around wanting to swing it. And you keep all of that on your arm while you're swinging with the armrest, which has a strap over the top that keeps it firm over your forearm, so you've got a fairly rigid setup, not too much slop for the user. And that gives you good ergonomics to be able to swing all day, for example, if that's what you're into. And finally, probably one of the things that we need when you're detecting is that you have the detector moving all the time. So if you've ever seen a new person using a detector, they just try and hold it stationary and expect it to work. The reality is you actually have to swing it from left to right in a steady motion.
And I guess there's a huge range of metal detectors out there, a huge range of technologies. But fundamentally, whether you're talking a pulse induction machine, which we use for our gold detectors, an old VLF single frequency machine or a newer multi-IQ machine, they all work on fundamentally the same principle. What happens is the metal detector creates a varying magnetic field. It does this by pumping current through the coil. And that varying magnetic field then creates what we call eddy currents. These are loops of current in the target. And those loops of current then create their own magnetic field, which the coil, the sensor, sees. And then the detector basically senses that changing magnetic field from the target and then turns that into audio. So fundamentally, all metal detectors work like that. They create a magnetic field, they just do it in different ways. That magnetic field then creates eddy currents in the target. Those eddy currents in the target then create their own magnetic field, which is then sensed by the detector. And when you think of it like that, it becomes really obvious as to the answer to everybody's most obvious question, which is how deep does it go? How deep does it go depends on how easily those eddy currents are created. A big flat plate of aluminium is going to create some really large eddy currents, really low frequency eddy currents because they're really large. A thin sheet of aluminium foil is going to create really small eddy currents because it's very thin, the material is very resistive, it resists those eddy currents. Or if you take that big same aluminium plate and turn it on its end, on its side, suddenly your aluminium plate has got big eddy currents like this. On its side, it can only create little eddy currents because those eddy currents are always created in the same plane. And so you can start to see that the depth of a target is going to depend on its composition, how easily those currents are created, its orientation, how big those currents are. All metal detectors then are working on that fundamental technology.
Can I maybe just another analogy that helps? We're probably going to use the term eddy current a fair bit in this presentation, which is probably a foreign thing for anyone that's not an engineer. But probably the analogy is if you're looking at a river and you've got deep water and it's the same eddy currents, you'll see a big whirlpool. So imagine whenever we say eddy current, we're imagining in the target something circulating. And if it was just a puddle, then you wouldn't have very good eddy currents. That's more like aluminium foil.
Yes.
That's really good. It's really interesting you say about that question about depth, because as a beginner and meeting other detectorists, it's quite a common thing. You're like, oh, how deep does this go? But it's interesting to know that it's as much about the object that you're trying to detect as the detector itself.
And it'll probably become a bit more obvious later on when we start talking about some deeper concepts. It's all going to come back to things like eddy currents.
Right, can I just ask for a bit more on, Phil, you just said something about pulse induction. What was that? You were talking about different types of, or is that too advanced for this?
No, that's fine. So I mentioned that everything depends on creating varying magnetic fields. A traditional detector, a single frequency VLF or CW detector, creates what we call a sinusoidally varying magnetic field. So the magnetic field goes larger, and then starts to die away.
Like a sine wave.
Smaller. Exactly like a sine wave. And then it goes negative, goes in the other direction. And that sinusoidally varying field is happening continuously. Whereas a pulse induction detector creates like a burst of magnetic field and then goes quiet and listens, exactly like a CB radio, for example, where you key the push to talk, you release the push to talk, and then you listen. Pulse induction detector works in the same way, creates this pulse of magnetic field and then stops and listens for the response.
Is that, I assume that's over like a micro timing though, is it?
Yes, absolutely. Yeah, very short periods. That's why actually on a pulse induction detector you can run what we call a MonoLoop coil, a single winding, because the transmitter is transmitting and then stops to receive. Whereas on a CW or a VLF detector, the transmitter is running continuously and the receiver is running continuously. So you have to have a specially configured coil such that the receiver can't see the transmitter while it's transmitting. And so we use a double D coil mostly in Minelab.
And probably just the general thing that a customer would need to remember is that pulse induction machines tend to be really good for gold because they just have maximum depth in various grounds, but they're not very good at discrimination, which we'll talk about later, which is deciding what's in the ground, whereas all of the CW, VLF, multi-frequency sort of coin and treasure machines, because they're constantly transmitting and receiving at the same time, you can do a lot more with that information to work out what's in the ground.
Cool. Can I ask what CW and VLF stand for?
Yep. CW stands for continuous wave, so it's a continuous sinusoid going into the ground, and that's exciting the coin or the target in the ground with the eddy current. And even while it's transmitting that sinusoid in, we're looking at the sinusoid coming back from that eddy current. So you look at both at once, and that's why it's called continuous wave, because you're continuously looking at the sine waves.
And VLF is very low frequency, so these are old sort of radio terms, just describing the frequency that you're operating at. CW was traditionally used to describe Morse code.
In this talk, we talk about CW and VLFs pretty much as single frequency detectors.
Right, okay. Paul, have you, as an experienced detectorist out using machines, have you kind of have you noticed a difference in using like pulse induction to like a VLF or a single frequency?
Yeah, well, the pulse induction are more specialised. They're not. The only time I really use one is on the beach, the GPX 5000. That one is what I use mainly for pure depth. When I know there's targets down there,
Yeah.
but the CTX or Equinox won't.
So it will get that extra because of the way that it functions.
Yeah.
Yeah. Oh, brilliant.
Punch down.
But it means you have to dig everything because it doesn't discriminate. It literally just has maximum depth detection and that's it. So it could be a rusty nail at 2 foot or a gold ring. You're going to have to dig to find out.
But your targets are relatively sparse at the beach, so it's not a bad choice.
Like you said about continually moving, why would it have to continually move?
It's to do with inside the detector, it's an electronics system and it actually drifts with temperature. So what does that mean? That means that if you were looking at the signal on your screen right now, you'd actually see it constantly like rising up like this and drifting away. So we have to do a thing called, it's very engineering, AC couple. So we actually take the drift out and make it look like something you'd expect to see on, a TV show. Just, the signal's nice and steady. So that process of taking that drift out, unfortunately means that the user has to keep moving and swinging.
Wow.
Because otherwise, if they were stationary, then taking the drift out would also take away their stationary signal.
And you'll actually find we allow that stationary version to occur when you're in pinpoint mode. And so you'll hear what we call a DC signal. You'll hear that constant signal while you hover over the target. But if you leave pinpoint mode on too long, you'll start to hear that drift occur. So that's why we encourage pinpoint mode just for short periods. So pinpoint mode will give you that DC operation, that static operation, but then normal detecting, you'll have that AC or dynamic operation where you have to be moving to see the target.
And some customers do get stuck, particularly new people. They think they get it in pinpoint and they don't realise that they've got to take it out of pinpoint. And then it stops working after a while because it's drifted off and it's lost its sort of lock.
That's interesting that you said about, so there's the change in voltage applied then between AC and DC. So DC is in pinpoint mode, is that right?
Yes. Yeah, in DC mode you hear everything, including that very slow temperature drift. When you go into AC, you remove that temperature drift, but you also remove the signal when you're just hovering stationary over a target.
That's like the difference between a motion and a non-motion detector then, isn't it?
Wait, yeah.
You're switching from one.
So does that, I've heard of motion and non-motion, is that the same then as AC and DC, or equivalent of?
Yeah, so non-motion would be the DC or static version, and motion would be the AC or dynamic version. Unfortunately, you're talking to two engineers, so we tend to come at it from the engineering perspective.
No, this is great. This is what we want. Right, so I've heard that now. So you can think about them in their different power sources, which is really good.
Yeah, so I can just talk a little bit about the main coil that you would see in the corner treasure space today. So for example, on an Equinox, it's got a range of what's called double D coils. So you've got one D this way, which is the transmit, and the other D that is the receive, and they're overlapped like that. So that means that where they overlap, where my fingers are hitting in the middle here, there's actually like a blade, and it's that blade that as a user sweeping over the ground, you've got to imagine you've got a blade of magnetic field that you're sweeping across the ground, and it's when that blade intersects the coin under the ground that you get a response and you hear it in your headphones. But probably one thing that a lot of people don't realise is that magnetic field drops off with depth quite quickly into the ground. It's almost a bit like an upside down pyramid coming out the bottom of your coil. So by the time you're getting down to about a foot, your magnetic field's only like the very tip of that magnetic field is left. It's almost all gone. And so the whole thing tapers down like an upside down pyramid. What that means is you've got to imagine in your head, if you're at your favourite detecting spot and maybe you've found some coins there in the past, and you really want to make sure you've found everything in that spot, so you're trying to do like a really thorough sweep, and some of the term they often use is called gridding it, because you're getting rid of everything in a nice methodical way. But you've got to imagine that actually at a foot you may only have the size of a small circle that you're sweeping underground, and so you actually have to have a lot of overlap of your coil swings. So what that means is every time you swing the coil from left to right, when you go back, if you step forward too much, you're going to be missing a lot of ground down at depth. It looks like you've got coverage on the surface, which you do, and your eye's very good at tracking that, but you've got to imagine in your head, actually, I need a lot more sort of repeating overlap as I move forward, and I have to move a lot slower if I want coverage down at, say,
I was
floor.
going to say that brings into play the swing speed as well, doesn't it? You've got to slow your swing speed down to let
It does, yeah.
to let everything happen. And
There's actually another artifact of the coil geometry as well. What Mark said was entirely true, but at very shallow depths, or sort of for a target on the surface, you'll see that the target at that blade in the centre of the coil, but for very shallow targets, you'll also see the target as you cross over the windings on the outer edge of the coil. So for a very shallow, small target, you'll actually receive 3 responses as the coil goes over the target. And so that's one way of identifying how deep a target is, just by the audio. Very shallow, you'll hear those 3 indications, and then at depths you'll only hear the 1, because you won't hear those outer windings again.
yeah, that's why I say it's the peripheral one. Sometimes you can go over a target, but you're hearing it beyond your coil
Right.
as you're swinging your
And you
coil
hear it
up.
on the rim.
Yeah,
That's fascinating. I love all those explanations, and I love the idea of almost like the icicle I'm imagining from beneath the coil, dipping down, and I think that's fascinating. And is that why, I think I'm right, I've heard this, whether it's true you can demystify it for me if I'm wrong, but a larger coil will often give you more depth. Is that because the diameter then tapering down is giving you that, or is that not necessarily the case? Because obviously if you've got a large diameter to start with, or could it be angled differently?
The answer to that is it depends, but let's assume the coil's exactly like a scaled up version of the smaller coil. What tends to be the case is the actual magnetic field is just spread over a larger area, and what that'll mean is you actually can see bigger targets. So going all the way back to that customer question of how deep does it go, is that my response to that it shows is always it depends. And so it depends. If you've got a big coil and you've got a big target, then you're going to see that deeper than, say, a standard coil. So that's true. Your guess that the field shape, that upside down icicle, it is the same kind of shape. Maybe the other way to answer that is if you went for a much smaller coil, you would have a smaller icicle, but you've got a lot more magnetic energy in that smaller area, which means you'll actually see smaller targets deeper. So
Okay.
it really depends. It's the sort of the allocation of all that magnetic field or energy and how that gets concentrated at the different depths, and how that, again, it comes back to how it couples with, say, the coin and what eddy currents it can get happening on it.
What your target is.
If we go back to your icicle comment as well, there's both stalagmites and stalactites. So as well as seeing under the ground, the coil actually is symmetrical, so it's seeing above the ground as well.
Now that I understand that a signal's being sent and received from a detector to once those currents are induced, it really made sense when you spoke about a double D coil and one sending and one receiving, because I just thought that was a design thing. I didn't know what the heck that was for. So now to know that one of them is doing that, it obviously makes sense why it needs to move now as well, because otherwise you're just sending a signal in one area and receiving it in the other, and you're not passing over the same space. So that kind of Venn diagram
Kind of.
area, or is that
Yeah,
wrong?
I mean, the Venn diagram is the blade, but when you've got that receive and the transmit, the two halves of the double D, the magnetic field is actually going down and up. It's like a continuous field that's set up between that RX and the TX.
Oh, so it's not quite what I thought then.
No. The takeaway you probably want is going back to pulse induction versus continuous wave. With continuous wave, we have to have a separate TX and RX coil. That's why we've got the double D, because we have to have continuously transmitting and continuously receiving. Whereas if you go to a PI, as Phil mentioned earlier, you can have just one single copper winding, and you can turn it on and then turn it off and listen. So you switch it from being a transmitter to a receiver in the electronics.
Yeah, so obviously the double D coil, transmitting and receiving, it still operates in pinpoint mode, in that static mode. It can transmit and receive at the same time and work while you're moving.
Amazing, thank you. I nearly got it.
Which is confusing with a concentric coil.
Yeah, concentric. I don't
Yes,
even know what
I
that
was going to mention that.
Oh, cool. Let's go for it.
So, so concentric coil is a round coil, and then it's got another coil in the middle of it. So they're no longer a Venn diagram with a blade. It's a Venn diagram where one circle's inside the other.
It's an egg.
And so you've still got, it's an egg, yeah, that's right. So you've still got a separate transmit and receive. It's just they're, I'll use a fancy term, superimposed. So they're sitting on top of each other now. And there are some trade-offs. Like if you go back more than a decade ago, concentrics were actually very popular in corner treasure. And they do have some benefits with having a more of a easier to use sort of localization of the target.
So very easy to pinpoint.
Very easy to pinpoint with, so customers really like that. But I'm not really sure actually what. We've moved to double Ds.
They don't have the depth of a double D. Double D is going to give you more depth.
And there's a few other little design trade-offs that engineers make when they're making a metal detector around concentric or double D.
Yeah. When you have concentric coils, because you've got one inside the other, that inner coil is very small. Whereas with a double D, you've got two relatively large, halves of that coil.
Okay, fascinating.
No,
really.
nobody asks for them now on a new machine anyway, do they?
Because of the depth, yeah.
No,
maybe.
because a lot of newcomers now don't realise you have other coil options. If you could have a concentric coil,
Right.
but they don't realise, because a lot of people, the first machine is either Vanquish or an Equinox,
Yeah.
which has got a double D coil.
Yeah.
Yeah, maybe they'll come back in fashion one day.
Yeah.
They have the uses.
Yeah, that sounds good. Well, if it makes it easier to find the target, it would be good to have that option if you had a site, I don't know, that you were kind of expected to find stuff on. But then I suppose you lack the depth. It's always a trade-off, isn't it? I
Yeah.
suppose, yeah.
What you've got to understand, Scott, is detectorists always want the best machine that goes the deepest and finds the most in a day.
Right, is there anything else you guys wanted to mention?
And the main one that we encounter as feedback is that the environment around us has a lot of electromagnetic energy from radios, smartphones, storms and lightning, electric fences. The LED lighting in modern houses these days is pretty nasty. All of that energy, unfortunately, can get picked up by your metal detector. And so you can have somebody that's never really used the detector much buy it from Crawfords and go out in the field the next day, turn the machine on, and it's just making all these crazy sounds. And because it's actually picking up the environment. And what you can do is actually do what's called a noise cancel, where you actually cancel all that environmental interference out. And then once you've done that, you can actually, maybe you're actually detecting near a village and it's quite noisy all the time. You've just got to realise you've got to drop the sensitivity back of your detector as well.
Okay, so is that the equivalent of, because I've worked in audio production a little bit, so that's the equivalent of like setting a noise floor or something like that?
Not quite. That's really a noise gate, I would imagine, where the sensitivity is like that, but the noise cancel is actually moving to a different room, for example, where you don't hear that noise. Yeah, so another analogy is CB radio. If there's a heap of traffic on one channel, then you'll just move to another channel where it's quiet, and that's essentially what a noise cancel is doing.
Oh, right, yeah. Okay, so it's like changing, like in acoustics, I know they have like a frequency of a room, and it's kind of like starting it again.
So we talked about double D coils. The double D coils obviously got an overlap between the transmitter and the receiver. So this also explains why sometimes you'll hear a sound from the detector when you impact a rock or a piece of wood or something on the ground, because you're slightly disrupting those two coils and they're overlapped in a very special way. You can start hearing those impacts through the sensor, through the detector system.
So thank you very much for joining us today. Thanks to Mark, thanks to Phil, thanks to Paul, and thanks to Minelab and Crawfords. If you'd like to join us on the second episode, we will be talking about target IDs and tones.